Good morning, ladies and gentlemen. So today, we are going to discuss the productivity measurement and quality management assessment case study of Group 4, whose members are Dimano, Mariel, Fedelo, Shaila May, Mendraz, Nayla, Rubio, Janelin, Tenorio, Rizaline.
So first, what is linear programming? As defined by the MindTools.com, linear programming is a mathematical technique that determines the best way to use the available resources. Before we discuss how linear programming is used to solve problem, let's first understand what kind of problems can be solved using this technique, linear programming. The first is, we need to understand the given problems and identify the basic elements to convert it to a linear programming problem. So here's our problem. A manufacturing company produces two items, product A and product B. The unit profit for product A is $6, whereas for product B is $8, and the resources are steel bars, centimeter, and production time, seconds. On an estimate, it takes 30 centimeter and 500 seconds to complete product A and 20 centimeter and 1000 seconds to complete product B. The company has 300 centimeter of steel bars available and must finish to produce items within 3.056 hours, 11,000 seconds. The objective function of the company is to come up to a decision on how to allocate the limited resources to maximize profit on a given time. Understand this well. Before we start, there are two aspects here, the formulation part and the solution part. Let's begin with the formulation part as we go through this example. We must find the maximum profit that company can earn with the constraint. The constraint here is the production budget. But how do we approach this problem now? First, let's represent this problem in a tabular form. Do you have any idea? Here it is. Let's go through it together. We must convert this problem into linear programming problem, and how do we do that? By writing the given problem in the form of mathematical expressions. Like in this problem, the company produces two products. The product A and the product B, as we don't know the exact quantity. Let us assume the quantity of resources to product A is X and the product B is Y. Can you tell me the total number of resources needed for product A and B to produce respectively? Right, it would be 30X plus 20Y. We're just multiplying the quantity with the required material. Next, let's look at with the constraint. It says that the production budget is 300 centimeter. That means the resources to be incurred should not be exceed to 300 centimeter. It can be less than or equal to 300 centimeter. Can you give it a try? Here's the answer: 30x plus 20y is less than or equal to 300 centimeter. This expression represents the budget constraint of the problem. The total resources should not be exceeded to 300 centimeter. Now let us express the total demand of the two products in a similar manner. You can do it. The combined demand of two products to produce should not exceed 11,000 seconds. 500x plus 1000y is less than or equal to 11,000. Therefore we use less than or equal sign to write this expression. And which constraint does this expression represents? Right, it represents the demand constraint of this case. This means if the company produces the products more than 11,000 seconds, they are not efficient to maximize the given time. Are there any constraints in the problem? Alright, we're all set. Let us now go to profit element of these two products. Can you tell me the objective of the company in the problem? The company wants to produce two products, A and B, that it yields maximum profit in each time. In simple words, the company would try to maximize the profit which can yield by the limited resources of A and B. Now, let's denote the total profit of the production. Can you try to write the total profit in a term of mathematical expression? The total profit can be written as this. It's the product of the quantity and the profit per unit Z equals 6x plus 8y. With this, we will write the objective function of this problem. The objective function in a linear programming problem is a mathematical expression of the ultimate goal. So, we have the two constraints here, the budget constraint and the demand constraint. This is how the whole problem looks in terms of mathematical expressions. This is the objective function. Maximize z equals 6x plus 8y. These are the two constraint, subject to constraints. There's just nothings we need to know here, and for that I want you to answer a question. Can a number of units produced by a company can be negative? That's right. It can never be negative, so we need to add the non-negative constraints. It can be written mathematically like this. It's very important to write the non-negative constraints on the formulation of a linear programming problem. Therefore, after we've discussed the meaning and formulation of linear programming problems, let us now move on how a linear programming is solved. So the question now is, how do we solve a linear programming problem? Well, there are different ways to solve this problems. The problems having two variables can be solved graphically, like in this example there are only two decisions variables, the x and y. For now we will be discussing the problem based on graphical solutions. To solve a linear inequality with two variables on a graph, we will use a coordinate plane. We know that there are four quadrants in a coordinate plane, as the decision variables in a linear programming problem should satisfy the non-negativity constraint. The values of x and y should not be less than 0. It means they will lie in a first quadrant only. Therefore, to solve this problem in a graph we need to use only this quadrant. For better understanding, let's solve our sample problem graphically. In this problem we need to find the maximum profit, which is denoted by the objective function z equals 6x plus 8y. Now let us find the values of x and y which satisfy these linear inequalities, as the solution is to be found using a graph. Let's represent these inequalities on a coordinate plane. How do we graph inequalities? We will first try the corresponding equations inequalities for this. Okay. Let's work on it together. These are the corresponding equations. These are now the coordinates of x and y-intercept. For the x-intercept we substitute y equals 0. We get the value of x is to 10, so the coordinates of the x-intercept are 10 and 0. And to find the coordinates of the y-intercept we substitute the x equals 0. That gives us the value of y is 15. So the coordinates of the y-intercept are 0 and 15. Similarly, we get the x and y-intercept of the second equation with these points. Let's draw two lines representing the two equations on a graph. Let's mark the 4 points first. The blue line represents the first equation, and the red line represents the second equation. So how will this graphical presentation help us find the optimal solution? Let's first mark the feasible region of this graph. Feasible region is the common region determined by all constraints of a linear programming problem. Each point of feasible region satisfies the linear inequalities of the problem, so let's mark the feasible region of this problem. With the constraints of our problem, the feasible region will get restricted to the region O, A, B and C. As you can see, the two lines intersect at point B 4 and 9. The region within this four corner points is the feasible region of this problem, as every point of this region will satisfy the linear constraints of the problem. Then how will we find the optimal solution? Since there are many possible solutions for this problem, we will use the corner point method to find the maximum profit. Now what's a corner point method? In this method the solution of a linear programming problem lies on the corner point of a feasible region. The coordinates of the corner points are substituted for the values of x and y in the objective function. In this example, points O, A, B and C are the corner points of the feasible region. We will evaluate the objective function by substituting these points as values of x and y one by one. First let's find the value of z at point O. The coordinates of point O are 0 and 0, so 6, 0 plus 8, 0 gives us 0. Likewise we will get the value of z as 88, 96 for the third and 60 for the fourth point, so we have all the four values of z at the corner points of the feasible region. Since our objective is maximize z, the optimal solution lies at point B 4, 9, because the value of z is maximum at point B. This is how we solve linear programming graphically. As have said by Mr. Keith Devlin, emeritus mathematician at Stanford University, the linear programming was and is perhaps the single most important real-life problem. That's all. Thank you for watching our video.